So let's talk about related rates. This is going to be 4 point. What section is this? 4.2 point something? 2.6. Related rates. Not 4. 2.6 related rates. So this is how we use derivatives to solve problems about the world. Related rates. So what is a related rate? A related rate compares the rate of change of two things compares the rate of change of two things to each other. A related rate compares the rate of change of one thing to another thing and compares these rates of change to each other. Okay. Compares the rate of change of one thing to the rate of change of another. Again, derivatives are all about change. Derivatives calculate change. So for example, let's see, what's a good example? If you change, for example, if you change position in space, you change your position with respect to time with 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 respect to time. So with respect to, I'm gonna abbreviate this WRT, with respect to time. So if you're measuring one example of a rate, right, is you're changing your position. Position we usually use S, sometimes X, and time is T. So this is going to be the change in the position with respect to time. Changing your position, your rate of change of position, compared to the rate of change of time, right? Maybe you go 3 inches, like you're a snail. You go 3 inches every hour. So changing position with respect to time. Change your position with respect to time. And we call this change of position with respect to time, we call this velocity or speed. Right? How fast you're changing, right? So we see a connection here. We have some kind of rate of change, or comparing a position with respect to time. So that's a related rate, right? Two things relate to each other, how one thing changes compared to how another thing changes. Change in position with respect to time, which in this case, the derivative of that is velocity. So we can change things, right? How things change with respect to time, or with respect to something else, right? And we can do this with any kind of thing, right? Usually it's we measure in terms of change of time. Most often it's in terms of change of time, but we can change any object with any one type of change compared to another kind of change. So for example, let's say the area of a circle compared to the radius. How does the area of a circle change as the radius changes? Right, you have the area of a circle, circle. Oh goodness. How does the area of a circle change compared to the radius of a circle? So we have a formula, right, that describes, that connects, we have this formula that connects area and radius, right? We know the area of a circle is, what was the area of a circle, everyone? Is that formula? Formula for the area of a circle? It's that funny one, wasn't it? Who remembers? Write it in the chat. Area of a circle was what? Something about pi. There's a pi in there somewhere. What was the area of a circle? Thank you, Paris. So yes, exactly. The area of a circle is pi times the radius squared. So we know we have this connection, right? This is a connection, connects the area to the radius. Right? This formula, or this description, says the area of a circle is found by this formula involving the radius. Take the radius, another measurement of the circle, and you square it, you multiply it by pi, and you get the area of a circle. And so we have this connection, right? These connected variables, these two connected variables, area and radius. And we can relate this rate of change by finding a derivative. What if I want to know how does the area change? Maybe how quickly does the area change compared to how quickly the radius changes? To find the rate of change of area compared to the rate of change of radius, we take the derivative with respect to time. What we will often be doing is we will be taking a derivative of some formula or some equation or some situation, take a derivative with respect to time. And we will find the rate of change, the change in amount of something, right? The change in amount of something. And like we said, the rate of change of two things together. So we find the change in the amount of area compared to the change in the amount of time. And we will get a formula for that by taking a derivative compared to the rate of change of the radius. So we're going to do d dt of this whole thing. We're going to take the derivative of this formula with respect to time, because we want to know how the radius changes with time. We want to know how the area changes with time. Every second, it grows a certain amount. Every minute, every whatever. And this is a related rate. So we're going to find derivative, right? dA dt, the derivative of the area, we're just going to say, well, that's dA dt. This is the change in area with respect to time. Change in area with respect to time. And it's measured in things like, meters squared per second. Let me write that a little bit better. Meters squared per second. It says time, everybody. So we have dA dt, the change in the area with respect to time. Equals. So we have our, how does our area change? How many meters squared, how many square meters or square feet per second does it increase or decrease? And now we have this other side, pi r squared side, and we need to do a derivative of pi r squared with respect to t, ddt. So we're going to use our chain rule. Just like before when we had like a y and we're doing dy dx, this r is going to do a derivative with respect to t. So we do the derivative of the whole thing, and we follow the same rules that we do normal derivatives for. We're going to take our power rule, we're going to take the 2, bring it in front. It's going to be 2 pi r, right? That's the regular outside derivative, times the rate of the radius changes per time, dr dt. Right? Just like we had in our implicit differentiation, same thing. We have this term here, this dr dt term, which represents the rate of change of the radius with respect to time. And so that's going to be something like, meters per second. Right? How many meters is the radius growing or shrinking every second? And so this is a related rate. Relates the changing area to the changing radius. And that's an example of a related rate. We can do calculations with this. We can do all kinds of explorations with this. But this is the idea. You are relating the changes of two things. Okay? What questions do you have so far about this? Any questions so far? So do you get the concept here of what's happening? Let me maybe show you. Let's draw a picture here. The dr, yes. The dr, this dr is because of the r of the radius, exactly. Because it's the change of the radius. At d, the d here stands kind of for like a change, right? Change in radius compared to the change in time. The rate of change, the speed of the increase of the radius, right? How much the radius changes because of the r. And just like we did with our implicit differentiation, when we did the derivative, we did d dt, it's really just like these pieces are like variables. They stick around. That's why it's dA dt, right? d dt of the area, the change in the area. And then we did d dt of r. Pi is a number, so it stayed. We did our power rule, bring the 2 down front. Then we had the r. And then we times by the inner part dr dt. Yeah, because of the radius. Other questions about what's going on here? So what does this look like visually? So say you have, right? Say you have a certain circle. And you say the radius grows. And now you have a bigger, really bigger circle. Right? And you see that the radius and the area, let me do these in colors. The radius, let me do the radius in green. Radius here. The radius here. Radius 1, radius 2, right? And then we have area 1 and area 2. So what we're looking at is you see that like a difference in the amount of increase, right? The radius ds and the area increase at different rates. They change a different like amount over the same period of time, right? Right here the radius is a certain amount and the area is a certain amount. Here the radius is a little bit bigger, but the area is a lot bigger. And so the area, I mean, clearly the area depends on the radius, right? But the amount of increase, how much the area changed, is a different rate than the amount of the increase of the radius, right? Those are like different amounts of change, right? It's like the area and radius grew, but there's a connection between them. We can calculate. We can know how quickly the area and radius change. We know the relationship between the change of radius, how this much change in radius will influence this much change in area. And that connection comes from the formula we have right here. The rate of increase of the area compared to the rate of increase of radius. And so we can understand those rates by this formula here. We can calculate those rates using the area formula and a derivative. We can calculate the rate of change of area compared to calculate those rates by using the area formula and finding the derivative. And this is the fundamental idea behind related rates, right? How the change in one thing can influence the changing of another thing. And this is the purpose or the function or the utility of derivatives. Measuring change. Measuring amounts of change, measuring and comparing change. A derivative is a calculation of change. So what are some other things we can calculate? Some other rates of change that we can connect, like we can relate to each other. What are some other rates of change that we can relate to each other? We saw area of a circle compared to radius. We saw position compared to speed. Weight and volume, yeah, for sure. That'd be one. So other examples, other related rates, related rates. We can have weight versus volume, right? Maybe we can have the change in weight over change in volume, right? Or maybe we can say weight has some equation times the volume, right? Weight, we can calculate the weight by measuring the volume of something times maybe like density, perhaps. Maybe this is like density. And we can do the change in weight with respect to time compared to some equation with the change in volume with respect to time. Yeah, how much like stuff you add. Maybe you like add more clay to something, adds more weight. Or maybe like a balloon, like inflating a balloon. How much does the balloon's weight change? Maybe like inflating a balloon. I like that. Inflate a balloon. How much does the balloon weight compared to the volume change? What are some other related rates we can do? What are the things we can compare to each other, like how things change? Weight and volume. We can do like, let's see. Other types of related rates. We can relate the volume. Here we go. The amount of water. Amount of water in a tub to the flow rate. Flow rate. Like how much, like how high you turn on the spigot. Right? If you turn the sink on slow, it's gonna like you're filling up a cup. It's gonna take a lot more time. Turn the tap on faster, it's gonna fill the cup up faster. So the amount of water at the volume of the water in a tub or a cup or whatever, compared to the rate of change of It's almost like volume, right? The amount of water. What other things can you do? What are some other things you might be able to calculate? Economy stuff? Yeah. Economy stuff is for sure important. Well, you can definitely try with some stonks, that's for sure. Let's see. You can do, some economy. Let's see some economy stuff. Maybe you can do the increase of economics. You can do the increase of, let's say, what is that? Like, you know how money sometimes, of inflation? Inflation with respect to, or compared to, actually compared to maybe something like GDP, your gross domestic product, how your inflation rate compares to the gross domestic product. Yeah, there's a lot of economics involving in math, and stock rate, sure, you can do that. Other kinds of related rates. You can do, there's a very famous, let's see. Okay. So there's the literally rocket science. Rockets. You can do the so when a rocket goes up, I don't know if anyone has been watching the SpaceX launches recently, but when a rocket goes up, it's changing velocity. Depends on the mass of the rocket, right? But when the rocket is, like, it's got fuel, it's got a bunch of like hydrogen, oxygen, fuel, liquid fuel in this rocket. And as the rocket uses up the fuel, it's lighter. And so as it gets lighter, it goes faster. So there's this rocket equation. The change of velocity compared to the change of mass as the rocket uses fuel. And so the rocket equation is delta V, or dV dt, the change in fuel, change in velocity, is, let me just make sure I'm getting this right, V ln m over mf. The exhaust velocity times the natural log of mo over m. Whoopsies. Or I should say maybe change in mass over change in time. So this is the change in speed. Change in speed. And this is the change in mass. Change of mass. And this is the exhaust velocity. Exhaust velocity. How fast it's spewing out its rocket fuel. literal rocket science stuff, everybody. That's what you know how to do now. And this is an ln, by the way, right? Right here. That's a natural log, ln, right? Thing we've seen before. That's the rocket equation. This equation and equations like it tell us how rockets get faster, how they slow down, how their speed changes depending on mass. So there are many different kinds of rates you can compare to one another, right? And this idea where we take a derivative of something, comparing, we have an equation, right? We figure out a connection between two things, velocity and mass, or inflation and GDP, or stocks and I don't know, amount of Reddit users that day, whatever. Some connection between two things. You take a derivative, some equation, you take a derivative of that equation, and then you compare the rates, how quickly they change. Like we said, volume and flow rate. You have area or volume and radius. Say you blow up a balloon, you can see how the radius changes compared to how the volume changes. So all of these are using derivatives to calculate the rate of change of these different objects. We use derivatives. This is, yeah, income to spending. Sure, like any relationship between two. If you can create an equation, connecting those two ideas, you can do a related rate for sure. Or here's another good one. Last example. Sorry, my wife is. We're going to end shortly, everyone. Last example is angle of inclination, let's say, to of a rocket, So let's say you're a little person, you're down here looking at a rocket, right? Here's the ground. Here's rocket ship. USA. And as the rocket ship goes up, right, the angle of where you're looking, this theta angle is going to change. Let me do that in red here. And it's going to compare to the velocity of the rocket going up. Yes, well, pardon my drawings. So we can have a connection here where we can measure things. And we have to come up with an equation to figure out how to connect these things together, right? So let's say we have the speed of the rocket, right? This velocity equation. Let's say that this one, and again, we're going to end here. We're going to get more into this next time. Say this is 50t squared. 50t squared is the speed equation, the velocity equation, and I want to know what is the change and what is the changing in the angle over the change in time? How do I figure out a relationship, right? What's the equation I can write that can relate this rocket speed going up to the angle that I'm looking at it on the ground? What is the formula? How do I connect these two ideas? How do I connect these two ideas? And the way we connect these ideas is we can make a little triangle. Let me do this better. I'm going to make a little triangle. We're going to use all the powers of our right angle trigonometry. Here's our angle theta. Theta in here. Theta in here. And then this is going to be, A, blue. This is A over here, and this is B. So this distance, let's say we're a certain amount away. Let's say we're 200 yards away, 2,000 feet away. 2,000 feet. We can connect with this. We can connect this theta angle and the speed of the rocket using a formula that the tangent of that theta angle is equal to the position of the rocket divided by 2,000 feet away. Right? Tangent of the theta, right? It's SOHCAHTOA. SOHCAHTOA, right? So here is a formula that we created a connection between the tangent, the theta angle. We found an equation that connected the angle here to the speed of the rocket, the position of the rocket going up. Position of the rocket going up. We created this connection. We see that the angle depends on the position of the rocket, and we know the rocket's changing position. It changes position with this formula here. It's going up this fast. And so we can connect this A value is not a certain set amount. It's a equation. It's a variable amount. And so it's a change, right? There's the rate. The angle compares, the changing of the angle connects to the changing position of the rocket. The rocket goes up, the angle will change. And those are the kinds of connections that we're going to be building using this. And then we would take a derivative of that. Tangent is secant tangent, or the derivative of tangent is secant squared, and ds dt, you take a derivative. We're going to get into all that next time. But I want to get you introduced to this idea of connecting two variables together with some equation. Sometimes the equation is the area formula for a circle. Sometimes the equation, did I write S? This should be not V here. This should be S here. S here. Position. Position of the rocket. Yeah, sorry. S here. And the angle theta here. Thank you for, yeah. So that's our connection, connecting these variables together. So we'll go over more of this over time. If we did a derivative, let's just quickly ddt this. We're going to get derivative tangent secant squared theta d theta dt. Why do we have this d theta dt? Well, because again, we're taking the derivative with respect to time, the rate, right? So the theta, just like our chain rule, we do the derivative of the outside, tangent to secant squared, times the derivative of the inside, that theta, just like our, I keep forgetting the name, just like the other derivatives we did. We have a d theta dt equals, here we got 1 over 2000 ds dt. Or, I mean, really, it's, you could think of it like it's ds dt over 1000, over 2000. Right, because this 2000 is like 1 over 2000, it doesn't change. So we get this connection here. We can find out how fast the angle changes, how fast the position changes. We have this connection. But that's the kind of thing we'll be doing coming tomorrow. So this connects the changing angle change of angle, which is d theta dt, to the rocket change of position. ds dt. Okay. So that's the kind of thing we're going to be building, these kind of equations, starting this week. This first formula, this formula, connects the, how do I say? Maybe I should say, connects the angle, or I should say calculates, maybe this is a better way to put it. Calculates, this formula here, calculates the angle, theta, using the rocket position S. So it connects, right? It calculates or it connects the angle theta to the rocket position. It connects those two ideas, and then we take a derivative and we get the rates of those connections. So that is a related rate. Question? It says connects. So we will be building formulas that connect these things. We'll be taking derivatives, talking about rates, starting starting Thursday. All right, everybody. Good job. I guess we went most of the time. 2 minutes early. That'll be fair. I guess we did spend some Rowan time today, so that's fine. All right, everyone. No homework. Just finish up whatever you got. I have graded all the things, so check your scores. And again, if you are missing anything... Oh, sure. Yeah, I have time. I just do want to say that if you're missing anything, get it into me as soon as you can. Thank you, Adrian. It's going to be a good luck. Yes, once you're done, if you're ready to go, say goodbye in the chat. Once you say goodbye, you're free to go. I'll see you all next time. Thank you very much. I'm going to stick around if you have any questions. Otherwise, have a great one.